It's very nice to be here in Paris, and springtime in Paris is very nice, especially. You've made the weather extra special today. I'm going to talk, after that very nice introduction by Professor Bard, about the paleo context of the climate changes and the role of the ocean in those changes. I'm going to stress here in this talk the variability in the deep circulation of the North Atlantic Ocean, and really to look at the changes, the variability that we see in the deep circulation on a much shorter time scale, really over the last 25 to 50 years is the extent of the record. Okay, thank you. First of all, a little background. I hope you will all learn some interesting facts about the deep circulation today. We don't often talk about the deep circulation in such detail, but basically as background, strong ocean currents primarily occur near western boundaries of the ocean, both in the upper thermocline, by that I mean above 1,000 meters depth, and also in the deep ocean. So you always go to look at the western side of the ocean when you want to see strong currents. The upper ocean currents, like the Gulf Stream, are well known. Now I'm going to concentrate today on the deep currents of the North Atlantic. And surprisingly, they're as big or even bigger than the Gulf Stream. There was a major effort during the World Ocean Circulation Experiment during the period 1990 to 2000 to measure the strength and structure of western boundary currents throughout the world ocean. And we have a kind of a schematic here summarizing the effort that was done. And what you have to realize is that we didn't, 25 years ago, we didn't have this detail in the ocean circulation. We didn't really know what was out there. So in the 1990s, we made measurements. Now this schematic shows the shallow or thermocline western boundary currents, like the Kuroshio here, and the Agulhas current here, East Australian current, Brazil current, and the Gulf Stream flow through Florida Straits in red. So those are the thermocline currents. We also have the deep current, the very deepest of the bottom currents, of lower circumpolar deep water. So this is water of origin in the southern hemisphere that flows northward, again on the western sides of the ocean. And we don't really have a name for these currents, although you can see they're as big as the surface currents. But they're not as dramatic influence on, let's say, shipping, so they don't have a name. So we call them, primarily we call them deep western boundary currents. And here we have the Antarctic bottom water coming up through the Atlantic. What I'm going to concentrate today on are the flow through the Atlantic of North Atlantic deep water, and that's in green. So this water, as Professor Bard said, is formed in the Nordic seas, north of Iceland, and in the Labrador Sea. And so in green, you can see that we have measured that current off the Cape Farewell in Greenland, off the Grand Banks, and then here, which I'm going to concentrate on today, off the Bahama Islands, and then down off Brazil in the South Atlantic. So that's I'm going to focus on those green currents, the flow of the deep western boundary current of North Atlantic deep water through the Atlantic. I thought here, in terms of variability, I was going to try to talk about a series of aspects, concentrating on the measurements off the Bahamas, about the boundary current transport, just how big it is and how we determine it. What is the boundary current variability? There's a certain recirculation offshore, which complicates the matter. And then to talk about the overall net transport, which is, I think, what the paleo perspective is interested in, is the size of that overall net transport. And finally, a little bit about the stability of the deep circulation. Could the circulation shut down. And so we're dealing really with this conveyor belt concept here in the Atlantic. Warm, I'm going to pretty much ignore the warm upper layer water that's flowing northward through the Atlantic and concentrate rather on this deep limb of the conveyor belt, this southward flow of North Atlantic deep water along the continental slope of North and South America. To measure that, there was an extensive effort by the group in Miami, led by Bill Johns, Tom Lee, Reina Zontop, and they put out arrays of instruments just west of the Bahamas. This is the Bahama Islands here, and extending outward. And this is just a timeline of the measurements that were made. They did it for 12 years, 1986 to 1997. And when you take all of those current meters, you basically they've put out arrays of current meters that look like this. This is a deep sea mooring. You have to realize these moorings are about 3 miles long. They're held at the bottom by an anchor and buoyancy at the top, and the stars indicate the instrument depths, the current meters, and then this is the structure of the deep western boundary current. I want you to focus on the area below 1,000 meters. So this is the structure of the deep western boundary current with a maximum flow of about 20 centimeters a second, or about half a knot current coming southward. But it's notable, I think the things that are notable about it is that it's relatively deep. It extends from 5,000 meters up to 1,000 meters depth, so it's 4,000 meters deep current, and it's very much confined within about 100 kilometers of the western boundary, so it's confined to the western boundary. And these are mean currents, so these are time average currents over the course of a year. And so this is typically the way we measure the deep western boundary currents. And the first idea is, what is the mean? What are the mean currents? And when we look at the mean currents, we can add them up. And so we call them, we do it in transport of sverdrups, million cubic meters per second. And here, off Abaco, the southward flow is 35 sverdrups, and that's 35 million cubic meters a second. For a kind of a conceptual size of that, the largest river in the ocean, largest river is the Amazon, which has a transport of about 0.3 sverdrups in comparable units. So this flow southward here is 100 times larger than the largest river in the ocean. So we have a very strong flow. Now, we've measured that in various places through the ocean, and I think there's two quite remarkable features. Is, first of all, this deep western boundary current actually is bigger than the Gulf Stream. So I know it's about the same size, but it's bigger. So, since I'm talking about the deep circulation, the deep western boundary current is bigger than the Gulf Stream. The second remarkable feature in these mean currents is that the deep western boundary current transport increases as you go southward away from the source. And that's quite remarkably different from the arguments, the dynamical arguments that were put forward about 50 years ago by Stommel and Ahrens, that the deep western boundary current, or the flow southward of the deep water, should actually decrease southward. In other words, you'd have a largest flow at its source region, and then it would gradually decrease as you went along the boundary. But instead of that, we see that the current actually increases southward. So that's something that we don't know. And I will say that there are things that, surprising things that we learn, which I try to highlight, but also the problems that we don't understand, the things that we don't understand. I would like to emphasize those even more so today. about the circulation. Now, if we go back to this array, over the 12 years that the array was out, there were on 2 occasions all of the instruments in the deep water worked, so that I've made a movie out of what the current looks like over that. I have to admit that I've not tried a movie before, but we'll see if it works. No. Sorry, I thought I had it all set up. No. Yes, I'm just... No. All right. So this, you can see on this diagram, I'll just talk while it's running. So this is depth on this side. It's a fixed array. You can see the moorings that are measuring currents. Basically, it's a time period during Watts. It was called Watts, Western Atlantic Transport Time Series. The distance here is the first 150 kilometers out from the Bahama Islands. And so on each day there are currents measured, and then I've just kind of interpolated and smoothed to make a movie of the current. And these are days, so the days are flashing. It's about 600 days in the movie. But the impression, what I want you to get out of it, is the impression of there are 2 aspects that I get when I look at this movie. One is that the western boundary current pulses. In other words, it becomes stronger and weaker. But then there's a time period when it kind of meanders offshore. Now this is the meander offshore, so the current's out here. We're not really resolving it, and the flow actually near the boundary is slightly northward. We think the current was still out there, but we didn't measure it very well. So it's meandered offshore during certain time periods. But if we go, especially in the beginning of the record, the impression is that the western boundary current is pulsing, stronger, weaker, stronger, weaker, so that here you see it's kind of pulsing back and forth, somewhat moving, and then meandering offshore. So there's huge variability in this deep western boundary current. And it's variability that we don't really understand what causes the variability. So this is the beginning of the movie, where I think it just shows that. So for about 200 days, it just is stronger, weaker, and so forth. So there's a kind of a variability in the deep western boundary current that we don't really understand. We don't really understand whether it's natural instabilities, whether it's wind-driven. Get back to where I was. Oh, that worked better than I thought it would. Thank you. So we don't know whether there are westward propagating eddies that impinge on the boundary and move it, make it meander offshore, or make it stronger or weaker. We don't know whether there are southward propagating continental slope waves, which is another mechanism for the variability. And finally, in terms of longer time variability, we would like to relate the longer term variability. So this is the transport during Watts, which is 1990 to 1992, the time period. So these are spheredrups. The mean southward transport is 34.5 spheredrups as shown. But these longer time period variations, we don't really know whether what we would like to do is relate those to variability in the source waters, which I think was implicit perhaps in Professor Bard's talk on paleo timescales. We would think that the strength of this deep western boundary current would be related to the amount of changes in the source water variability. As I said, there was another period which was called the ACCP, Atlantic Climate Change Program 3. And you can see there's actually, I should say, there are two ways you can do transport, just to kind of say there's a complication even in calculating transport. Basically, the black line is adding up all of the velocities when they're southward. So that's the southward transport. And then there is a way, but you can imagine that sometimes there is northward flow as measured by the array. And so the total flow as measured by the array, adding up all the northward and southward flow, is shown by the lighter line. So there's a complication in how even with a fixed array of current meters, how you estimate the transport. Again, I say we don't know what the variability is, what causes the variability. There's no obvious seasonal cycle which is what all scientists look for initially. We don't know about how much of the variability is caused just by the offshore meandering, which we don't know what causes that. We don't think it's related to Gulf Stream transport or to wind stress curl. We don't have a long enough record to see if it's associated with the North Atlantic oscillations. So there's a lot of things we don't know about the deep western boundary current. Now, one of the complications when one wants to go to the kind of paleo perspective, which is what I would say is we're talking about the net southward flow, the overall southward flow through the Atlantic in the deep limb of the thermohaline circulation. So what happens with this, with the western boundary current, is that we have a strong current near the Bahamas, but there's what we call offshore recirculation. There's northward recirculation offshore. So the deep western boundary current, confined right close to the boundary, is bigger than the net northward flow. And if we look at the arrays, the Miami group spent a long time trying to measure this recirculation. They kept going further and further offshore. So they started in the beginning with just short arrays to measure the deep western boundary current. But because the deep western boundary current was bigger than the overall southward flow, they kept going offshore, further and further offshore, to try and capture the recirculation. And I think by and large they did not succeed. This is the picture, the structure of the deep western boundary current. Again, it's the same inside the first 150 kilometers. It's exactly the same as I showed you before, with the mean deep western boundary current well defined here. But then offshore of that, you see there's northward flow. And it's not a structure that's very well defined going out to nearly 600 kilometers offshore. There is northward flow, and it's not a sharp recirculation. And this is overall the structure we get. As we accumulate the transport, we get to 35 Sverdrups at about 200 kilometers from the boundary, and then it starts to come back. So by the time we've gone to 600 kilometers, the net southward transport is about 22 Sverdrups. But this figure doesn't give you a feeling that we've gotten to the end of the recirculation. They needed to go even further with the moorings to determine the overall net southward transport associated with this deep limb of the thermohaline circulation, or the conveyor belt. What is perhaps surprising is that when we go out to measure this southward flowing deep western boundary current, we can measure it because in its confined position, it's relatively straightforward to go out and measure it. But the southward flow in that boundary current is bigger than the net southward flow when averaged over the basin. So we don't know what sets the size of the transport of the deep western boundary current, and why is it so much larger than the amount of water flowing southward. And we don't really know how much of the southward flow recirculates northward from these measurements, and how far offshore does the circulation persist. So the second problem when we look at a conveyor belt like this, if we're trying to address the kind of overall role of the ocean circulation, we'd like to know how much overall net southward flow is. If we just measure quite close to the boundary, we're going to get a much larger conveyor belt, but then we're going to have a lot of recirculation in the interior. And so the problem in terms of addressing the size of this thermohaline circulation is to try and estimate the overall southward transport through the ocean in the deep water. Basically, to do that, I think it probably, from my view, from watching the Miami group try and measure the recirculation, is we came to the conclusion that it was virtually impossible to go. You couldn't go far enough unless you went all the way across the ocean. You had to go all the way across the ocean to measure the total recirculation and therefore the net southward flow. So basically, we've taken the view that you've got to measure the whole basin circulation. You've got to go all the way from Miami to Africa to measure the circulation to get the size of the net southward flow in this thermohaline circulation. And the traditional way that we have done that is to look at hydrographic sections, is to do a hydrographic section from coast to coast across the Atlantic Ocean. And in fact, really, the conveyor belt, this picture is really based it's fundamentally based on these global hydrographic sections that had been made prior to prior to the period when this was put up in about 1990. So it is based on hydrographic sections. Now, if I just describe what we do with the hydrographic section and there have been 6 hydrographic sections here going all the way across the ocean. They were made in 1957, 1981, 1992, 1998, 2004, and 2010. So we've done 6 of these hydrographic sections across this ocean, across the Atlantic. We basically go across the ocean and we make hydrographic measurements. It's CTD profiles, temperature and salinity profiles at about 125 stations distributed across. You measure top to bottom temperature and salinity, and from that you make geostrophic calculations of the geostrophic current profiles. We adjust the reference level, which is has been a historic problem in geostrophic calculations of current. We adjust the reference level to basically conserve mass across the ocean, and then we can quantify the net, the zonally averaged southward or northward flow in terms of depth or in terms of water mass type. So we make a zonal section measuring temperature and salinity top to bottom, calculate the geostrophic velocity, and then we quantify the flow. And this shows the 6 profiles. These are the 6 zonally average profiles of north-south velocity. And so you see here above about 900 meters, the southward flow. That's the net northward flow in the upper limb of the conveyor belt. You can see it varies somewhat from section to section. And then below about 1,000 meters, we have this general southward flow in all of the in all of the hydrographic sections. And this is the North Atlantic deep water that's coming southward. Primarily, that's the water that's coming southward in the deep western boundary current, but then some of it's recirculating back. But because we've gone coast to coast, this is the net amount. So this is the south minus the north, or the sum of the south and the north, to give you this net southward transport of North Atlantic deep water southward. And then down deep, you see a little bit of Antarctic bottom water going back northward in the ocean. So we can do it in depth classes. And primarily, I'm going to talk about upper and lower North Atlantic deep water. The upper North Atlantic deep water, we've not quite arbitrarily, but we've set a limit in depth at 3,000 meters, 1,000 to 3,000 meters. So that's what I'll call upper North Atlantic deep water. It's primarily the water that's formed in the Labrador Sea. And then the lower North Atlantic deep water is 3,000 to 5,000 meters depth. And those are the water mass types that have been formed in the Nordic seas, north of Iceland. So we can split up, we can look at the variability in these water masses as a function of depth, or we can break it down into water types. So these are the classical names for water: Antarctic intermediate water, Labrador sea water, Iceland, Scotland overflow water, Denmark Straits overflow water, and Antarctic bottom water. And these are the diagrams for the 6 sections that we get. And I'll show you a table, but while I've got this up, one of the remarkable features, I think, in these sections is that there's quite a bit less of this Denmark Straits overflow water, or lower North Atlantic deep water, in the more recent sections. There's been a noticeable drop. And in fact, the conveyor belt model of Broker, or when it was quantified by Schmitz and McCartney in the 90s, in the early 1990s, is based on a kind of a southward flow of order 12 sverdrups for this Denmark Straits overflow water, when in fact more recent sections suggest it's more like 6 sverdrups. So it's about the present conveyor belt model, especially for the Denmark Straits or the Nordic Seas overflow water, is only about half as large as these diagrams that we're typically thinking about the size of the overturning circulation. If we look at the properties, this is from recent papers submitted to Ocean Science. It's in Ocean Science Discussions by Chris Atkinson, who was a student in Southampton. So he's quantified for each of the sections, it tabulated how much flow of upper North Atlantic deep water, that is Labrador sea water, and how much lower North Atlantic deep water, which is what I'm concentrating on here, what the variations are in terms of the transports. And basically, we have relatively constant amounts of upper North Atlantic deep water coming back of about 12 sverdrups. And the lower North Atlantic deep water changes, you see after the first 3 sections, decreases quite a bit. Chris Atkinson has looked to I just see if I go there. I'm sorry, that one was a bit blurry. It's a trade-off between the way the picture looks. The lower North Atlantic deep water, the 6 values, he's tried to correct them for any seasonal effects. But you can see the lower North Atlantic deep water was much stronger southward flow, and then in the more recent sections, and he's put error bars on those transports. Not really significantly different or significantly outside, but in fact, the more recent measurements of the lower North Atlantic deep water transport are notably smaller than the earlier values on which the conveyor belt are concepts or sizes of the conveyor belt are based. So on the basis of 6 hydrographic sections, and that's really the classical way of defining how large the overturning is, the net southward flow of lower North Atlantic deep water has decreased from the classical value of 12 sverdrups to about 6 sverdrups. And the southward flow of the upper North Atlantic deep water, or the Labrador Sea component, has stayed reasonably constant at 11 sverdrups in these sections, but the most recent section suggests a stronger southward flow in the Labrador Sea water. In terms of looking at the deep circulation, we've started to monitor the Atlantic meridional overturning circulation since 2004 with the rapid array of moored instruments across the Atlantic. Effectively, the array represents a continuous hydrographic section. It's a coast-to-coast. The measurements are coast-to-coast. It's based on geostrophic calculations. And although it doesn't look like a hydrographic section or analysis, it effectively is. We have a series of moored instruments on the western side, on either side of the mid-Atlantic ridge, and then on the eastern side of the ocean. The primary measurements for the bulk of the ocean are temperature, salinity, and pressure measurements on these moored time series, which give us basically a permanent hydrographic station at the western side and at the eastern side from which we can calculate geostrophic currents. And then we add in direct velocity measurements in the kind of wedge region right near the western boundary to make sure that we resolve the strong deep western boundary current near the boundary. So that we are, in effect, continuously monitoring the overturning circulation coast and in a coast-to-coast way. And so on this figure, which I didn't discuss the first half, there is every day, there is a profile of the zonally averaged northward flow that are shown in the gray here. And so you see the envelope shows the variability in those profiles on a daily basis. And then underneath in colors are the hydrographic sections, the 6 hydrographic sections that have been made. So you can in a sense, see where the hydrographic sections estimates fit within the envelope of this variability with time. And what I was trying to say when analyzing the hydrographic sections is that these profiles for the early hydrographic sections are right way off on the edge of the variability that we are observing on a kind of a daily basis. So they're not outlandish, they're not out of possibility, but remarkably, the 3 early sections sit way out on the boundary of the variability that we measure in this net northward or southward flow. From these diagrams, again, because we now can look at them kind of in depth pattern, in depth classes on a daily basis, we can make daily time series of, this is the upper North Atlantic deep water, the lower North Atlantic deep water, and the Antarctic bottom water are shown here. It's a record that goes from 2004 to 2000, almost the end of, to the end of 2009. And so you can see the variability on kind of a daily basis, the 10-day average and then 30-day low passed beyond that to look at the variability in the southward transports. I would say you don't see, there isn't really any trend over these 5 years in the lower North Atlantic deep water. It's just that the old sections in 92, 81, and 1957 would all be kind of almost, they'd correspond to these very sharp peaks. It would be quite remarkable if they were down there. So it's what I would say is the lower North Atlantic deep water is consistently about 7 Sverdrups. There's a lot more variability in the upper North Atlantic deep water. And we can look on a daily basis of estimates of the variability. This is a lot noisier plot. These are basically the top. This is the thermocline transport, 0 to 800 meters. The green is the intermediate water, which is small. The upper North Atlantic deep water in blue, you can see huge variability in the blue. And then the lower North Atlantic deep water, the one that we think has reduced over time, is in the darker blue. Again, these are 10-day values and then 30-day low past. What we see here in terms of the variability, we see that the lower North Atlantic deep water, there are actually time periods when the lower North Atlantic deep water doesn't flow southward at all, that there's no, for short time periods. The first one was in 2004, we noticed an event where there was no southward transport of lower North Atlantic deep water. Recently, we've been having more and more of these events of no southward flow. What's shown in the band here is that actually these are year-long averages of southward transports of the lower North Atlantic deep water, and note that in 2009, 2010, the transport was quite a bit reduced. It was down to only 4 Sverdrups during that kind of whole year-long period, but it's recovered. So we're seeing interesting variability in the deep water flow, in the deep water circulation. In terms of the overturning, the other kind of product that we're getting out of RAPID that one most often sees is we are measuring the Gulf Stream transport in blue, the Ekman transport in black, the southward recirculation in the mid-ocean, and then we sum those up. So this is a measure of the net northward flow in the conveyor belt. The conveyor belt is shown in red, which we call the meridional overturning circulation, the strength of it. And quite remarkably, in this 2009-2010, it was about 30% down on previous values over a year long average. And we're struggling a little bit to quite understand what it means when the overturning circulation stops. All right, so there is a kind of time period during just at the end of 2009 to transition to 2010, where actually there was no net northward transport of upper layer water. Overall, the Gulf Stream was low, the recirculation was stronger, the Ekman transport was southward instead of northward, and we had no no net northward transport in the upper layer circulation. So the overturning, the Atlantic meridional overturning circulation stopped for a brief period during 2010. On a year-long average basis, the overturning circulation was 30% lower during 2009, 2010 than it had been in the other 5 years of the record. The southward transport of lower North Atlantic deep water appears to be only half of its classical value that you will read in most papers. Then the net southward flow of lower North Atlantic deep water has stopped on several occasions. So that all of these kind of features make one ask the question, might the Atlantic meridional overturning circulation stop? Is the present overturning circulation capable of being shut down, of being in an off state? And so this is a kind of an issue about the stability of the circulation, the stability of the conveyor belt, or the stability of the deep circulation. And that's the last topic that I wanted to say some words about. We have theoretical arguments made by Dijkstra and Dryfout, really building on the same arguments that Ramstorff made in the 1990s, that the freshwater transport associated with the Atlantic meridional overturning circulation determines whether the overturning circulation can exhibit multiple equilibrium. And it's a kind of a theoretical argument. And Dijkstra and Dryfout are working with a quantity called what they call MOV salinity transport, which is really the freshwater transport associated with the overturning circulation. So does the overturning circulation transport fresh water northward or southward is fundamentally what the argument comes down to. And if the overturning circulation, the theoretical argument is that if the overturning circulation exports, I'm sorry, I've got to get this right, if the overturning circulation transports fresh water southward, then the theory suggests that the MOC, the Atlantic meridional overturning circulation, is capable of multiple equilibrium. It's capable of switching from on to off if it transports fresh water southward. And the argument, if I can just try to paraphrase what I think is the argument is if you had a freshwater event in the northern Atlantic, capped the North Atlantic with fresh water so you couldn't do the deep water formation, and you shut down the deep water formation and the overturning circulation no longer would be able to take fresh water southward, and so you would amplify that off state so that it would stay off until something else happened. But you would keep it in an off state if it does indeed transport fresh water southward. So to look at this MOV salinity transport, you might say, well, it became quite an issue. Dijkstra came and gave the Rapid Group a talk in 2006. We decided the way we would address that problem was to look at the freshwater transport at 24 South in the South Atlantic to see what the overturning circulation does in terms of freshwater transport. So we made a section along 24 South, a hydrographic section on board James Cook in 2009, and we also got an earlier section in 1983 made on Oceanus. That's the profile of the section. We choose this section. Later we're going to hear about the exciting and energetic region around further south in the Atlantic with the Gullis leakage coming around the tip of South America. We decided we couldn't do the hydrographic estimates of the freshwater transport down there because there would be too many eddies, too much variability. It would be too exciting for us, really. So we decided we would do the section at 24 South, repeating the earlier section, because it's not a region of large eddies. It's more of in the subtropical gyre circulation. It's a section where you can see the sloping thermocline indicating equatorward flow in the thermocline. You see some Antarctic intermediate water. You see all the classic things. This is the deep water flow along the western boundary. Again, salinity. I just show those. It's classic hydrographic measurements. We use these stations to do the geostrophic circulation, just as I was discussing at 25 North in the Atlantic. And we look at the zonally averaged circulation so that we look at the structure of the north-south flow as a function of depth at 24 South. And I just want to show really to say, first of all, that the traditional view, if I talk to my classically oriented colleagues in oceanography, the traditional view is that the Atlantic Ocean is an evaporative basin. And that so there's a net evaporation over the North Atlantic, and the argument is that that's why it's so salty. The Atlantic is much saltier than the Pacific Ocean, and one of the arguments about why that is because there's a large net evaporation over the Atlantic. And in terms of the conveyor belt, we have this idea that there's a northward flow of relatively fresh Antarctic intermediate water from the Antarctic northward through the South Atlantic and into the North Atlantic. It's relatively fresh water, and then the evaporative basin of the North Atlantic converts that fresh water into saltier, lower North Atlantic deep water. As Professor Bard said in his talk, he called the deep water salty, high salinity, lower North Atlantic deep water. So that's the concept of the conveyor belt in terms of its freshwater budget. And so we tried to test that view by looking at this circulation at 24 South. So this is the 24 South. And basically this curve, I'm not sure if I've got this quite right. This is the curve of the velocity structure as you come down. So that's northward flow above about 1,200 meters depth. And then you see the southward flow. And then it's a bit funny here, but we got the Antarctic bottom water seems to be in some sense above the southward flowing, but that's a question of in the deep flow, that's a question of the topography. But if we just concentrate here on the upper water flow, so this is the upper water flow going northward above about 1,200 meters. And I've color-coded the waters so that in red are the waters saltier than 35 parts per thousand. So this is, in red, is the water saltier than 35. And then the intermediate waters are fresher than 34.68. That's a convenient way of defining the low salinity intermediate waters. And you can see that the deep waters basically all have a salinity quite close to the average of about 34.85 parts per thousand on this section. So the southward flow is all going south at about let's call it 34.86. So the question is, are these waters saltier in terms of a transport-weighted basis? Are these waters saltier or fresher than this lower North Atlantic deep water? Well, if we look at it, the northward flow is dominated by the salty thermocline water, 10.6 Sverdrups versus 8.1. So there's more of the saltier thermocline water that's clearly saltier than the deep water. And then there's there's a substantial amount of intermediate water flowing northward, and it is fresher, much fresher than the deep water. And so what we do when we quantify what the Dijkstra and Dryfout call the MOV salinity transport is we quantify this by multiplying the transport by the salinity and averaging that. If I show you the Oceanus section, it's a slightly reduced circulation, but again, we have more northward transport of the salty thermocline water, 8 Sverdrups versus 5.7 Sverdrups of the fresh intermediate water. And so we have a similar circulation both in the 1983 and the 2009 sections. And so from those two, we try to quantify the MOV salinity transporter. And it works out that the freshwater transport, if we go to the bottom line here, in both of the two sections, the freshwater transport is southward, associated with the overturning circulation. The northward flowing water in the South Atlantic at 24 South is effectively has higher salinity than the southward flowing North Atlantic deep water, which is different perhaps from the classical view of how the Atlantic circulation works. And these are in units of they are effectively freshwater transports of about 0.13 spheredrops or 0.09 spheredrops. That's a kind of amount of additional fresh water that has to be added in the region north of 24 South to convert the northward flowing upper waters into southward flowing North Atlantic deep water. So the overturning circulation itself, by our estimates, actually transports fresh water southward in it. Now, the one complication and the one, so now that's my result, I suppose. I want to say, we think the overturning circulation transports fresh water southward. The complication is that on top of the overturning circulation, you have a subtropical gyre circulation, which typically has evaporation in the tropical regions and precipitation in the polar regions. So you have another component of the freshwater budget at a latitude like 24 South. And when you add that in, we would say that the North Atlantic, the Atlantic Ocean north of 24 South, actually does have a very small net evaporation of about 0.1 spheredrops of fresh water. So there is a net evaporation, which is more than compensated for by the shallow subtropical gyre circulation, whereas the overturning actually requires a net input of fresh water to balance the freshwater export southward. So, in the sense, I mean, it is common. It is a common belief that the Atlantic is a great evaporative basin, more evaporation than precipitation and runoff. I think the models are generally forced with about 1 spheredrop of net evaporation over the North Atlantic, over the Atlantic, let's say north of 24 South. The analysis, not only this analysis, but other analysis by Saunders and King and McDonough and King, Weyer et al., have, I think, shown quite clearly on the basis of oceanographic measurements that there's only a very small net evaporation over the Atlantic north of 24 South or 30 South. If there is a net evaporation, it is very, very small. In terms of our calculations, I think we're quite clear that the MOV salt flux is definitely negative. That is, there is a southward freshwater transport associated with the overturning circulation. The upper layer northward flow across 24 South is saltier than the southward deep water flow, return flow of the North Atlantic deep water. And the waters flowing northward are dominated by salty, salinity greater than 35 parts per thousand, upper thermocline waters. And they dominate the the northward transport of fresher intermediate waters. Now that saltier water, seems clear that it must come from the Agulhas region, and we'll hear about the Agulhas region this afternoon. There is no water as salty as 35 parts per thousand in Drake Passage, and so when we're saying that the source of this northward flowing thermocline waters across a section like 24 South has come around the tip of South Africa from the Indian Ocean. And in terms of the overturning, the freshwater transport on the basis of the theoretical models and the theoretical arguments, the present Atlantic meridional overturning circulation appears to be capable of multiple equilibrium, and it could shut down. And one of the things I like to say about the rapid measurements, the rapid array, is we're out there watching, waiting for this overturning to shut down. Thank you.